ORBSLAMMER. ORBSLAMMER.
This is an introduction to the ORBSLAMMER localization service, which is a standalone implementation of ORBSLAM running without any visualization. So it doesn't require any GPU to visualize. It doesn't require any visualization libraries. All the visualization is done within the browser. So instead of having all the dependencies that you usually have to get ORBSLAM running, you have a simple app image that you can run on any x86 Linux distribution, and you just connect your browser to an internal web server that will then use Three.js to visualize what you usually get, like if you use it in ROS or with the built-in visualization. You can download the app image directly from the GitHub repository. You just download the app image, make it executable, and can immediately launch it. You download the app image from the GitHub repository and also the ORB vocabulary, which you don't need to know what you need it for, just download it, put it somewhere, you can reach it, and also download the example configuration file, which is in localization service example.yaml. This file contains camera parameters, but you don't need to worry about those. Just leave the file as it is. As sources, you can currently use either a Video for Linux device that is directly connected to your computer. In our case, we're going to use the Virtual Beast because it has a webcam between the eyes. It's announcing itself as a simple USB webcam, but you can also use any HTTP MJPEG stream. So if you have something like Droidcam, where you use your phone as a remote camera, or any other stream, you can use that as well. First parameter is the vocabulary. Then the path to the example YAML file. Again, just use the one that's provided. And then the camera URL, which is either a full URL, which will be like HTTP something, or a simple integer, which is the index to the Video for Linux device that you're using. We're going to be using Video for Linux /dev video 2, which we can shortcut by 2, or you can use the full path to the Video for Linux device. Again, we're going to use 2. When you launch it, you get a lot of output for the initialization. You can either control it from the command line, but that's not what we're going to be interested in. It does tell you that it's going to run a web server on the port 11142. We're going to connect that in the browser, and you get this relatively simple configuration interface, which gives you control over the tracking, over the maps it's going to create, and the camera calibration, and you can visualize the current state. Let's do the calibration first. You get the usual checkerboard pattern. You will have to measure how big one checkerboard element is and then put it in here. I don't know the exact number yet. I'm just assuming it's 2 centimeters, but use something that's correct. Sure. You will see the output of each captured frame. It's a bit cumbersome at the moment because you have to capture it and then you have to look if it's correct. Let's capture a frame. You can see it captured the frame. It did the edge detection, the corner detection for the calibration. So this is a valid frame. We have to do that roughly 10 to 15 times to get good calibration. If you're familiar with how camera calibration works, then you know that you should make sure that you have all areas covered. So let's do it. 10 to 15 good ones. Once you're done, you compute the calibration, and then you have the safe, is there a safe calibration here? So the next time you're going to launch the localization service, you can just click on apply and reload an existing calibration, so you don't have to calibrate it every time. Now up to the how the tracking works. We have two different modes, mapping mode and localization mode. The idea behind it is we are going to, the project is going to use it in a way where you can create a map of a room once, and then you can reuse this map to localize without changing the map to make it more predictable. But the official ORBSLAMM mode does continuous mapping, so it will keep adding to the map, which you may or may not want. In our case, we don't want it. We want to specifically remap something if it has changed, and if it hasn't, we want to use an existing good map without destroying our existing map. So since we don't have a map yet, we need to create one. There is another important thing to consider here, which is allow new maps. So ORBSLAMM 3 does create small individual maps if it loses tracking for a short period of time. And later on, when you revisit that same area, it tries to combine them, which is called loop closing, or local mapping. So it tries to find overlapping areas and then create the combined map. You may or may not want that, depending on if it provides the result you want. We will keep it on for now. By default, when you're starting the localization service, the mapping is not running. So you have this button resume here. What we're going to do is we're going to place our camera somewhere and resume. So it will start to look for features, and as soon as it found the match, it starts mapping. So you can see we now have 3 keyframes in our map. You don't, the biggest problem we currently have is we can't read the IMU of the Vitura glasses, which means all the motion estimation where it tries to figure out how the camera has moved, to figure out where to look for matching features, is done purely by visual features, and especially when the map isn't all that good yet, that doesn't really work all that well, or when the camera has slow shutter speed. So this should improve in the future, but it does support the use case where you don't have an IMU, and in this case we just have to be very slow, very deliberate on what parts we are viewing. So what I'm basically doing now, I'm moving it in a parallax, basically horizontally, like a baseline in a stereo camera, which gives me a nice depth between the frames. And if you want to know what the tracking state currently is, you can go a real-time visualization, the Open3D viewer. In this case, you can see the camera here, and let's rotate that. So that's our camera. We can move it around a bit, tilt it up. The map is not that good yet, so the tracking is very choppy, but you can already see moving according to where our camera is moving. Also, the frame rate of this virtual camera is not all the best. By default, we have this movement scale here, which just exaggerates the coordinates, because otherwise the movement would be so small that you can't see it. So if we go down to a scale of 1, it doesn't really move all that much. And by default it's 10, so that you can actually see it moving a lot. Let's move forward. You can see here the position, the quaternion of how the orientation is. You can see if it's tracking or not. The interesting thing here is if you click Visualize Map, because that will load the current keyframes and map points, and you can visualize it here. So not much to see yet, because the map is still pretty small. Now let's go back. And now we're going to show what's happening when you're losing tracking. So let's go over here. Now it lost the current track. It started a new map. Let's wait until it has 10 keyframes, and then let's slowly rotate back to an existing, to the thing it's already seen. So, because 10 keyframes is currently the cutoff, anything below 10 keyframes, if you're losing tracking again, it will just discard it because that map doesn't have any valid information in it. So let's slowly rotate back and let's hope it does find enough matches to run the loop closing. No guarantee. Yes, now you can see it. Okay, and they immediately lost the tracking again. So this merging of the maps probably caused it to create such a bad map that it couldn't locate itself anymore. Again, that's like we have a very simple scenario. But for this, in this case, this is why we have this allow new maps off, because what you can do when you switch the maps off is it will not create new maps. So it will constantly try to, okay, probably just died. Okay, so again, we now have an empty state because it's not running. We are applying the current calibration and we are turning new maps off. This means when we now start mapping, we have some keyframes. Yes, now we have some keyframes. Let's make 10 so it doesn't discard it immediately. Okay, so now if it loses tracking, it doesn't do anything anymore. Let's see the 3D viewer, which will tell us the pose has been lost. Nothing's going to happen. But now if we go back to a space it already seen, it will relocalize itself. So the good thing there is now it does continue to improve the map, but it will never create a new one. It will always only use the existing one and keep adding to it. So if you're losing tracking, you're creating two bad maps, it will not be able to merge two bad maps. It will only extend the current map, which for us is an important feature. Which means, and that's probably if you're doing a manual map creation is the more logical thing, that if it loses tracking, you just go back to where you know you had tracking instead of creating a new small map and then trying to merge it based on bad features. So you can see it's working quite nicely. Now let's visualize what we've created. Let's build a bit of a better map. Let's make some forward motion just to give it some enough poses to do some 3D reconstruction of the map points. Okay, now we lost it. Again, it does not create something new. We go back to somewhere we already know, and it relocalization is also pretty fast, so it's much more desirable than creating the new map. Let's see if we can reconstruct the table here. Again, this would be improved if we had access to the IMU of the glasses, because this would mean it can understand that the glasses didn't actually move all that much, instead of trying to extrapolate the movement of the glasses by this choppy localization. Let's see if we get some. Yeah, now we get something of a bit of the table. In this case, the map it creates is relative to the first time it got a match. So if the camera wasn't perfectly aligned with the floor and at some random location, it will rotate, the map will be rotated. In our case, it's rotated a bit downward because I had the glasses a bit facing down, which for the visualization doesn't matter, but if we want to use this map for actual navigation or mostly robot navigation, then we need a map that is aligned with the floor. And for that we have two ways to do that. We can either use the sliders here and pitch it up, down. Maybe just like roughly align it. Or once we have something that is relatively good aligned, we can use auto detect floor and it will try to do it automatically. So this is our map. Positioning is now relative to the floor. So if we move forward, we should actually, so the y coordinate stays the same, as good as I can hold it with my hands. We can also use some funny view where we see the first person view of that. This is going to be interesting later on for some AR thing we are working on. We're moving forward, we're moving backward. Okay, so now let's see what we can do with this map. So now the map is only existing in memory, but obviously we want to, once we have created a good map, which can be quite some work, we don't want to lose that. And currently we have a map with 61 keyframes, 2600 map points. What we can now do is, let's first pause it. So now we are no longer doing anything. We can download our headless. And now let's kill the tracking again. So it's not running. Start it again. Let's keep the camera here. So we can see there is currently no map in here, but we can select the map we just stored. And we upload it. Upload is, the atlas is uploaded, so we have our 61 keyframes again. Now what we can do is switch to localization mode, because we don't want to create an additional map. We want to reuse the existing map and just use it to localize. Apply the camera parameters. And now let's resume and go to 3D viewer. So we lost our pose and we got it again. Now we are in localization mode. Let's visualize the map again. This is what we stored before. Again, here are the flowers on my table. This is my laptop, and we are localizing us in our map. Now this is all nice and everything for testing, but you obviously want to use it somewhere in some software. Let's kill it. And that's where the REST endpoints come into play. All the visualization that's done with this built-in web server are available as for you in any other software. So you can start the mapping, load the map, get the pose as server-side events, all via calling into this backend. So you can call it from Python, you can call it from, in our case, JavaScript. And now you have this localization running in its own standalone localization service, which you kind of do not need to worry about. You just have it running and have it running on a strong PC or anything. And then you have your system that is using this localization service and gets the pose out. At the moment, it can only use streams that are connected directly to the localization service. So you have to tell it what the camera it is, where it's taking the camera frames from, either the Video for Linux device or a stream. But in the future, it will be possible to send the camera frames also via REST endpoint directly to the localization service. So you'll be able to take whatever frame you're getting from whatever device you have and send it there. And this will then be integrated into the tracking. But again, for now, it's only using cameras that are connected to the localization service directly.